I'm excited to talk about the creation of the universe and how it's transformed over the 13.8 billion years it's been around. Hopefully all in 10-15 minutes. The universe began as a Big Bang. The technical name for the Big Bang theory is the lambda CDM, or lambda C cold dark matter. Lambda being dark energy, which causes the universe to expand. Cold dark matter being the substance that holds galaxies together. The Big Bang theory is not an origin theory. It does not claim to know how or why the Big Bang happened. It only goes back as far as the actual creation of all the energy in the universe at one point in time, and that's the Big Bang. And then from that point forward, it looks at that energy in the universe and describes how it's transformed itself into our present universe. And we can look at the various stages that the universe goes through by the era. The Planck era is the furthest back in time we can go, 10 to the minus 43 seconds. All the energy in the universe was created at that time. We rapidly go through the grand unification era where the strong force and gravity and the forces start to separate from each other. The inflationary period is a very important period in time where the universe in a period of microseconds expands by a factor of 10 to the 26. That's a huge amount in a fraction of a second. This inflationary period, at the end of it, the universe is approximately the size of a grapefruit. It's 10 centimeters across. Still extremely hot. The universe continues to expand and cool. It goes through a quark, hadron, and lepton phases. In these phases, the particles of the universe are formed and are around for the first time. A very important phase is the nucleosynthesis phase, because in essence, what happened with the Big Bang is at the time of the Big Bang, only two things were created in the universe, and that's hydrogen and dark matter. Two things, and two things only. At this point, when the universe is between 3 minutes to 20 minutes, the universe is cooled to just the right temperature that nucleosynthesis can occur, i.e. the perfect temperature that hydrogen can be converted into helium. That you can get nucleosynthesis, nuclear fusion of hydrogen into helium. And at that point, by weight, 25% of the hydrogen in the universe is converted into helium. So at this phase now, what we have in the universe is only three things. We have hydrogen, helium, 25%, and we have dark matter, which by weight far outweighs both the hydrogen and the helium. So we have only those three things, hydrogen, helium, and dark matter. This is during the phase of nucleosynthesis. So what is the universe at that stage? How are we going to conceptualize it? For now, well, I just think of it, for now, just as a big ball, like that, with only those three things happening in it, hydrogen, helium, and dark matter. During the photon phase, the universe is so hot that you have photons there, but all the matter in the universe is ionized. So it's either as a hydrogen plus, or there's electrons, which are negative. And it's so hot and so dense, even though you have photons everywhere, the photons can't go anywhere because they keep bouncing off the ions. So the universe during the photon phase is packed with photons, everywhere photons, but the photons bounce, bounce, bounce. So if we're looking at one photon, it doesn't go anywhere. That's one photon, and all the photons in the universe are doing the same thing. They're just in this dense soup and just sort of bouncing around like that, going nowhere. So the universe is this expanding pool of matter in the form of hadrons and leptons, and photons, but the photons aren't going anywhere. They're just bouncing around. And the universe is, meanwhile, continuing to expand. And as it expands, it cools. And as it cools, obviously, different chemical reactions are going to take place when there's cooling. So the next most important phase happens and starts at around 300,000, from 240,000 years post-Big Bang to 300,000 years. And that's the phase of recombination and decoupling. And what happens there, and this is very important, is that at that point, the universe is cooled enough that electrons can join up with hydrogen. So now we have hydrogen and an electron joining up, and that forms a neutral hydrogen. And the same thing with helium. The electrons will join, will merge, and you've got a neutral particle. And suddenly, neutral particles permit light to go through. And in other words, the universe becomes transparent. For the first time, the universe is transparent. And all those photons that were always there, bouncing around, suddenly are released. And they start to travel out. Wherever they are, suddenly they're released. Their last, as they were bouncing around, their last direction, they're released and they travel on. So everywhere in the universe, from every point in the universe, photons going in every direction from every point in the universe that they've released when the universe is transparent. And what are these photons that are released? Well, you've probably heard of them. This is the famous cosmic background radiation. And the cosmic background radiation is the radiation, the photons that were bouncing around there like crazy while the universe was expanding, and then finally when the universe became transmitted, they were released for the first time, and then they start to travel across the universe in all directions, permeating in all directions. But of course, because the universe is expanding, they're getting stretched, but we'll come to that. We just have to know at this point that the cosmic background radiation has been released, and think of it, that's the only light that's in the universe at this point, is this light that's now been released by the cosmic background radiation. Why do I say that? Because at this point, there's no stars in the universe, right? We've had this hot mess, but the universe is cooled. Now we're left with this light that's been released, but what else is in the universe is just hydrogen and helium and dark matter, and that doesn't generate light. In other words, there's no stars, so there's no light in the next stage of the universe, and that's why it's called the Dark Ages. The Dark Ages are when the universe consists only of hydrogen, helium, and dark matter. And of course, you've got the cosmic microwave background radiation trend, light going through it, but in terms of matter, you just have these things, and they don't generate light. So the universe is dark. It's an expanding entity full of this cloud of stuff, but it's dark. There's no more light being generated. So when does this light get generated? Well, let's start looking now at details of what actually happens with the matter and the hydrogen and the helium, because I sort of simplified everything, making you think that everything is actually, quite uniform. But what happened was, because of quantum fluctuations, if you will, when the matter and energy was thrown out into the universe, it wasn't thrown out perfectly evenly. It was thrown out in clumps. And so you had clumps of matter, and they tend to be in sort of net-like distributions. Clumps of matter. And these clumps of matter, when we zoom in on one clump of matter, well, that ends up turning into a galaxy. There's enough matter clumped that those clumps actually end up forming the galaxies within. And so let's look at it now, a very close-up of these clumps. We're going to zoom in on one clump, which is one galaxy, and just analyze what's happening in one galaxy at that point. Well, when the Big Bang happens, what's thrown out is the hydrogen, the helium, and the dark matter. And the hydrogen, the helium, and the dark matter are going to be sent out in spheres, big blobs, rotating spheres of hydrogen, helium, and dark matter. What popped out of the Big Bang, yes, is totally random and chaotic. The only thing that's not random and chaotic is that these blobs that were thrown out, within each blob, everything in it, the hydrogen, helium, and dark matter, are all spinning coherently. So the universe would have one blob, one galaxy, everything would be spinning like this coherently, those three things. You'd have another galaxy over here, maybe smaller, spinning maybe in a different direction, of course. It's a completely random process. You'd have another galaxy over here. It's a big ball of hydrogen, helium, and dark matter. And it's spinning. Maybe it's spinning, all in this direction. All kind of random sizes, all kind of random spins, directions of spins, probably rate of spins, all kind of moving kind of in random directions, some approaching each other, some moving away from each other. But the only common entity within them all is the hydrogen, helium, and dark matter that they're composed of, all spinning coherently. So what does this mean? What does that do? Well, the important thing here is you have to know about accretion disk physics. Accretion disks are the builders in the universe. The solar system is an accretion disk. The rings of Saturn are accretion disks. All black holes have accretion disks. Whenever you have angular momentum and gravity combined, you get accretion disks. So here we have dark matter that doesn't interact gravitationally with itself, and the hydrogen and the helium, all like in this galaxy, let's say spinning like this. The dark matter, the gravity acts as if it was right at the center, applying like Newton's shell theory. Everything within the shell, it helps, it's as though it was at the center, the distribution of the dark matter. So it's spinning around, and the hydrogen and the helium start to compress down to the equator of the spin of this particular galaxy. Over here, it would be like here, whatever the spin is, down to the equator would come the hydrogen and the helium. But most importantly, at the same time, and even before that, this period of reionization, even before while this hydrogen and helium is starting to come down to the center, in the very center of every single galaxy, you have a collapse of hydrogen, helium, and dark matter, because the density of it is so high at the center of these galaxies that you have very early in the universe collapse of hydrogen, helium, and dark matter into supermassive black holes. Every galaxy has a supermassive black hole. Supermassive black holes are a completely different category of black holes to ordinary black holes, which are millions of times smaller, and there's millions of black holes in a galaxy, but only one supermassive black hole. They're completely unique, and that's because they form very early in the universe from a direct collapse of a huge molecular cloud. They don't go through any star formation like other black holes. They're completely unique, and every galaxy has one. And they're supermassive, but they're not massive enough to accrete a spiral galaxy. They're just not big enough, as big as they are. Yes, they're going to control what happens in the local vicinity, and you'll get a local accretion disk around the supermassive black hole, which of course is going to depend on the supermassive black hole. But then a spiral galaxy is also going to form around this supermassive black hole, with the driving force being the dark matter, the coherently spinning dark matter, which, by the way, remains in a spherical orientation, continuing to spin like this, while the hydrogen and helium start to compress. So as the hydrogen and helium start to come down like this, they're also clumpy in nature, and enough hydrogen and helium clump together to form a star. So then you start to get the stars forming. But of course, when the stars form, they're going to form in a beautiful spiral shape, because you're going to get a spiral galaxy, and the orientation of the spiral galaxy is going to depend on the orientation and spin of the dark matter, not the orientation and spin of the supermassive black hole, because in fact most galaxies, the supermassive black hole accretion disk and the spiral angle do not coincide. They're often off. So the supermassive black hole does its own thing, if you will, in the center, but the galaxy is controlled by the dark matter spinning around and around. So that's an individual galaxy. But really what I'm really excited to talk about is something even more important, and something that is not talked about in physics and not talked about in astronomy, and that's the shape of the universe. You would think that something like the universe, if it's an entity, it should have a shape. Yet, if you try to even consider this matter, it's like, whoa, no, not allowed. For example, I quote from Wikipedia, if you talk about the shape of the universe. It says, well, if it has a shape, then it has an edge. But, and I quote, spaces that have an edge are difficult to treat, both conceptually and mathematically. Namely, it is very difficult to state what would happen at the edge of such a universe. For this reason, spaces that have an edge are typically excluded from consideration. Interesting. Because it's hard, it's not even considered. Well, what would happen at an edge? But then you're stuck with the idea that you have to have an entity that has no shape. And what entity can't have a shape? I think the universe has a shape. And we can start with another person who thought the universe had a shape, and that's Albert Einstein. Albert Einstein published General Relativity in 1915. In 1917, he published a very important paper called the Cosmological Considerations of General Relativity. And in that paper, the point of that paper was he wanted to consider the shape of the universe. He said, well, given general relativity, what is the shape of the universe? What do my equations predict? And he went to the astronomers to get some help. And unfortunately, the astronomers gave him some bogus information. They thought at the time, from their observations, they thought the universe was static. Nothing was really moving around much. And they assured Einstein that the universe was static. And so Einstein obviously wanted his equations to fit the evidence. And so he took his general equations and applied them. And given that he had to make the universe static, his analysis showed that the universe should be like a big sphere. His universe was essentially a static sphere. And the reason, but he also reasoned that if it was a static sphere of matter, because you have gravity, and if you have matter in a static sphere, and all matter attracts all other matter, a static sphere could never just be stable, because everything would attract and it would have to implode. And so he thought to himself, well, I'm sure the universe is a static sphere, yet it's not imploding. There must be something causing it not to implode. Let me make something up, and we're going to call that the cosmological constant. It has to be there, he reasoned, because otherwise the universe would be imploding. And so he, even though he said right in his paper, I hate to do this because it's out of nowhere, I'm going to introduce this into my equation to explain why the universe, my static universe, is not imploding. And, but unfortunately what happened, of course, 15, 20 years later was Charles Hubble proved that the universe was expanding, at which point Einstein called this his biggest blunder, introducing this out of the blue to explain the static universe, because he didn't need to explain a static universe, because the universe, of course, was not a static universe, it was expanding universe. But very important things came out of Einstein's paper. And one of the important things that came out, and I'll quote right here, is Einstein looked at what happens to light at the edge of a universe, because that was a big problem. But he did the math, he did the analysis, and I quote from his paper, thus a point of mass can never leave the system, And a more detailed investigation shows that the same thing applies to light rays. A system of the universe with such a behavior of the gravitational potentials at infinity would not therefore run the risk of wasting away, which was mooted in the Newtonian theory. So in other words, at the edges of the universe, light was not escaping. And mass or light cannot escape at the edge of the universe because it's drawn in by the universe itself. So if we think of Einstein's model, but apply the obvious evidence of an expanding universe, what are you left with? I argue that the obvious answer and the intuitive answer, and it in fact explains what happens at the edges answer, is the right one. And that is an expanding shell. The energy and mass in the universe was formed at one point and then expanded out, and the form it's going to expand out in is a shell, an expanding shell. A typical example of that, an expanding shell in the universe, is the most important type of supernova, called a type 1a supernova. In a type 1a supernova, you have a small white dwarf dead star orbiting with a bigger star that's not dead. There's matter that feeds off from the big star to the white dwarf. The white dwarf is slowly increasing in size. As soon as it reaches the Chandrasekhar limit, the white dwarf implodes and detonates a nuclear chain reaction so that all the energy, all the matter that was there in the white dwarf gets blown and put into pure energy and expands outwards from there. Nothing left at the center. You have the energy there, the matter there, turns into pure energy. And what shape does a type 1 supernova take? Well, of course, an expanding shell. What you would naturally expect from anything that begins as an entity tied together and then is all expanding out from there, it has to expand in the form of a shell. Nothing left at the center, but coming out like this is a shell. But then you ask, but again, you ask me, but what happens at the edges? What's going on at the edges? The edges are not a problem. The edges are not a problem because of the gravitational lensing of the universe itself. And we're going to look at that in detail because that's the important thing here. If we look at an expanding shell universe, so the universe is like that and it's expanding as a shell, and now we're going to look in detail at a close section, very zoomed in section, and we look at what's happening to galaxies. Let's look at a galaxy right in the center of the shell. All light rays and photons are going to emanate in certain directions based on the gravitational field determined by general relativity. That's the shape of the tapestry you see imaged when you're like the bowling ball in the center. So based on the shape of that, light rays are going to always emanate in certain directions. Now what happens is, as light rays start to get close to the edge of the universe, there's all the universes in here, light rays can't go where there's no matter or energy. They're attracted to matter and energy. Just like you can have a black hole and you have light that circulates around the black hole like that and like that. Light goes where the matter goes. It's attracted to matter gravitationally. So it can't exit the universe. So any light ray like that goes that way, and like that goes that way. So these are light rays like emanating from the central thing. Okay, no problem there. But what happens with a galaxy, let's say here, let's say you have a galaxy there, and you have observers in that galaxy there. There, the curvature and the lensing of the universe itself is so great that right away you get light going like that. So when they think they're looking out into the void of their universe, because the universe is expanding this way and they're looking out and they should be seeing a void, no, they're seeing light that's like come this way going out is the same path it takes going in. So light rays are very extremely warped there, as opposed to there, there, and then even over here it starts to go like this, and over here it starts to go like this, so it can't exit that side of the universe either, so it gets arched back around. In other words, for all observers, no matter where you are in the universe or in the shell, here or in the center of the shell, the universe is always only the shell. You can only see back along the shell because that's where all the light bends, because that's where all the matter is. So the expanding universe is expanding and it's taking all of this with it. It's all moving together. And you're seeing in all directions, but you're not seeing in all directions. All directions are always going to be back and forth along the shell. And that explains what happens at the edges. So in this theory of the universe, it's not a complex, tricky, how do you imagine it? Is it a four-dimensional hypersphere? How many dimensions are we talking about? No, it's none. It's like it's simple 3 dimensions. You have an expanding shell, expanding shell, expanding shell. The universe is always only within the shell. And what happens, for example, then for the cosmic background radiation in detail, at all points in the universe, let's say when the expanding shell universe at this phase, when there's recombination and the universe becomes transparent. So at every point in the universe, this cosmic background is released and starts to go out in all directions. Go out in all directions from every point. Go out, but as I showed you with the diagrams, it's going to follow the same thing. It can't ever get out from the shell, so it starts to follow like this. So all 3 dimensions are always back along the shell for everyone. So the universe at this point, when it was 300,000 years old, recombination, the universe was 3,000 degrees Kelvin temperature. So that's the wavelength of the light when it was emitted everywhere, here, follows a perfect black body spectrum, meaning that the peak is at 3,000 when it's emitted. But of course, photons don't behave any rules. They're random, and there's going to be a distribution of photons. Some are going to be 4,000, some 5,000, some 6, some are 2, but the distribution is going to be a perfect black body distribution. And the universe between then and now has expanded by a factor of 1,000 times. It's 1,000 times bigger, which means that the cosmic microwave background radiation was stretched 1,000 times. So its temperature has gone from 3,000 to 3 degrees Kelvin. So when we search out into the universe, it's 3 degrees Kelvin. And just one more little added detail, and that's if we zoom in, just one last zoom in at a galaxy. Let's say there's a galaxy there versus not at the time of recombination. When the light gets emitted, but it's near a galaxy, the cosmic background radiation, and starts to come out, it also gets redshifted, but this is a gravitational redshift because it's leaving that galaxy and going into like space. So it gets gravitationally redshifted as opposed to the background radiation that leaves and isn't redshifted. So that this light coming from thick galaxies is going to be slightly cooler than the light coming where there are no galactic structures. So there's going to be a slight discrepancy in the temperature of the cosmic background radiation, which is the classic picture you see, where you see sort of the spotted image, because where it's from a galaxy, it's going to be slightly different than not. So the Big Bang, the universe is an expanding shell. Within the shell represents all three dimensions, no matter where you are in the shell. Looking at what happens to light at the edge of the shell, just as Einstein did, is not really a big problem. It's not something to be afraid of. And when you can get past that hurdle, then you can talk about a universe which has an actual shape, such that I think that there's a void in which it's expanding into, which contains absolutely nothing. And so it's infinite. You can have infinite nothingness. But the universe itself is a finite object, infinite to our eyes because it's expanding. One last thing, I'm glad I forgot to mention this. A very important thing, because the two sides of the universe are expanding so rapidly, they're not causally linked. Because if you looked at Newton's shell theory, you would think that anything inside the shell, there would be zero gravity, and everything outside the shell would be enormous gravity, according to Newton's shell theory. But Newton's shell theory doesn't apply if the two sides of the universe are expanding away from each other at faster than light, which they obviously are, because for example, down in this period already, it increased by a factor of 10 to the 26 in a very short period of time. So expanding faster than light, so the two sides are not causally linked. So the gravity and the light, this part of the shell is going to be affected only by the shell in this area, and not by the universe over there. The Big Bang, the big expanding shell universe theory. Wow.